friends of mathematics from around the world, a very warm welcome. My name is Kumar Murthy, and I'm the director of the Fields Institute for Research in Mathematical Sciences. On behalf of the Institute, thank you for joining us at the public opening of the 2020 Fields Medal Symposium. Although we're meeting remotely, I wish to acknowledge this land on which the Fields Institute operates. For thousands of years, it has been the traditional land of the Huron-Wendat, the Seneca, and most recently, the Mississaugas of the Credit River. Today, this meeting place is still the home to many Indigenous people from across Turtle Island, and we are grateful to have the opportunity to work on this land. There are many things that bring people together: shared interests, shared goals and aspirations, shared values, shared joy, and even shared tragedy. What brings us together today? Obviously, it is our shared interest in mathematics, not just as an intellectual pursuit, but as a symbol for the aspirations of the human spirit towards knowledge and towards overcoming obstacles. It's about the creative journey of the human spirit, wanting to peer beyond the known, wanting to push back the limits of our knowledge, of overcoming difficulties and dealing with setbacks, and of ultimately achieving new successes. It's the human story of how mathematics is done, as captured in the achievements of 2018 Fields medalist Alessio Figali. Alessio was awarded the Fields Medal for his contributions to the theory of optimal transport and its applications in partial differential equations, metric geometry, and probability. Some of you will know what those words mean, and some of you will not. But just as we're able to listen to and enjoy beautiful music without necessarily knowing all the technicalities of the composition and orchestration, we can all share in the delight of Alessio's accomplishments and how he got there. The Fields Medal and the Fields Institute are both named after John Charles Fields, a visionary Canadian academic, who felt that communities that had been driven apart by political and social issues could actually be brought together through mathematics. Nations that had been driven apart could once again learn to cooperate through mathematics. And young people especially would propel this cooperation forward. Both the medal and the Institute recognize the importance of young researchers, mathematical scientists who are at an early stage of their scientific career and who show great future promise. Each year, the Fields Institute hosts over 150 workshops, conferences, seminar series, outreach activities, graduate courses, and special lectures. And each year, it draws close to 10,000 participants from around the world. All of this activity would not be possible without our many enthusiastic and generous supporters. The Fields Institute receives generous funding from the Province of Ontario, the Natural Sciences and Engineering Research Council of Canada, the Canadian Institutes of Health Research, the National Science Foundation of the United States, and the Simons Foundation. We're also supported by 9 principal sponsoring universities across Ontario, 11 affiliate universities, corporate partners, and generous private donors like many of you. We are deeply grateful to all of you for enabling us to do what we love most, the study and communication of mathematics. This year, with the pandemic, our events have shifted online. This is our first year holding the Fields Medal Symposium online. Though we lose the opportunity to interact in person, we can connect with an infinitely wider audience around the world. Consequently, this year's symposium will include speakers in Switzerland, England, France, the United States, and Canada, and will have a truly global audience. We're grateful for the opportunity to reach mathematics enthusiasts the world over. Once again, I thank you for joining us for what is sure to be a wonderful event in celebration of mathematics. We begin our program with a message from Her Excellency, the Right Honourable Julie Payette, Governor-General and Commander-in-Chief of Canada. The Governor-General will be followed by His Excellency Claudio Tafuri, the Ambassador of Italy to Canada.
Bonjour. Hello, everyone. My name is Julie Payette, and I am the Governor-General of Canada. Greetings to you all, attending this year's Fields Medal Symposium, which is being presented virtually for the first time ever. due to the global pandemic our world is still battling. In front of you, I know I am preaching to the converted when I'm talking about how important math is and how much fun it is. You already know that. But you also know that math has a kind of reputation out there in the general public for being a field that people either hate or find difficult, if not completely incomprehensible. Yet, the truth is that everyone uses math every day at the grocery store, for their home finances, or whenever one has to use proportions or count on a certain chemical reaction to occur when baking or cooking something. People read about math every day in the newspapers, in the likes of surveys, studies, percentages, or trends, and they understand it all. So why is math so feared? Outside the circle, of course. I think that perhaps people don't realize that everything is about math. That the way the integrated circuits in their cell phone work, the explanation of why objects heavier than air can fly, and how an eye doctor can come up with the exact right prescription for a patient to see better, that all of this can be described using the one true universal language, the language equally understood by all in the entire world, math. And this is exactly what we are celebrating today. Math and the talents of those Canadian mathematicians whose contributions and pioneering work have pushed the boundaries of the field. Like this year's Symposium's honoree, 2018 Fields medalist, Alessio Figali. Congratulations, sir. Le Symposium est non seulement la tribune par excellence pour mettre en valeur les mathématiciens canadiens de talent, mais aussi pour explorer les impacts des travaux, comme ceux du lauréat de la médaille Fields de 2018, Alessio Figali. Bravo, monsieur. Et merci à la communauté mathématique internationale de participer en si grand nombre à la toute première édition virtuelle de cet événement. In Canada, we have long relied on science and data to inform our decisions. The COVID-19 pandemic has made that even more clear. Whether you represent government, businesses, or even just a family unit, we all need facts and rigorous analysis and collaboration and information sharing to make better decisions. Les faits et les données, la rigueur et la collaboration sont clés pour nous permettre de prendre de meilleures décisions. Par chance, en science, nous parlons tous la même langue, le langage universel des mathématiques. That unity, that commitment is exactly what we need to tackle global challenges, from climate change to pandemics. We also need to encourage brilliant young minds to consider careers in science, technology, engineering, and math. Your contributions and their future contributions are vital to solving the most pressing issues impacting our planet. Thank you to all of you within the Canadian and international mathematical community for tuning in and celebrating math proudly and unequivocally. J'espère que vous profiterez des jours à venir pour élargir vos réseaux et pour célébrer nos importantes réalisations en mathématiques et en sciences, peu importe où vous vous trouvez. Bon symposium à tous. Prenez bien soin de vous. Take good care of yourself. Stay healthy. Au revoir.
Your Excellency, the Governor General, Director Mathy, distinguished professors and researchers, dear students, good afternoon. It's a pleasure and an honor for me to speak to you today at the inaugural event of the 2020 Fields Medal Symposium dedicated to Alessio Figali and his work. I'm proud and I'm glad that the Fields Medal was awarded to Alessio Figali, the second Italian to receive this prestigious prize since Enrico Bombieri in 1974. John Charles Fields created this prize in 1936 at a time of great political turmoil in the world, inspired by the idea that through science you can put countries together. And today, more than ever, As we depend on science to face the extremely complex global issue, his view is not only timely but necessary. Alessio Figalli is a researcher who was entirely educated in Italy at the University of Pisa and at the Scuola Normale Superiore di Pisa, under the supervision of internationally well-known professors before arriving at the ETH in Zurich. This is a clear sign that mathematics in Italy still has something to say, but in order to have something to say, you must devote yourself to your studies, make sacrifices, and also not neglect the apparently distant discipline of the humanities. Science and culture are in fact founding elements of our civilization, and these elements have enabled us to dialogue and collaborate above and beyond our national borders. It is important that a discipline as fundamental as mathematics remain alive and creative. It is a discipline which seems remote and abstract to many, but which is instead concrete enough to create a universal language and to find solutions to global issues and challenges, such as the pandemics we are facing today. Research must be a strategic objective for an advanced country, as it is a key factor in economic development and social progress. And it is of great importance that we work together in order to make sure that young researchers can realize their aspiration and potential. The fact that the Field Medals is awarded for exceptional achievements made by promising mathematicians under 40 show us how crucial it is to put sufficient trust in the intellectual abilities and the positive energy of the young generation of researchers. And we do need to trust them. Our own future is based on their visionary work, studying theories that have yet to be proven. Let me conclude with my very best wishes to Alessio Figalli for his exceptional career, and my congratulations once again on the work and commitment which have earned him this very important distinction. And to you all, I wish a very fruitful symposium and much success in your research. Thank you and good afternoon.
Thank you, Governor General, and thank you, Ambassador, for your words of welcome and support, and for illustrating the full and meaningful role that mathematics and the Fields Institute play in forming strong international connections and in addressing the global problems that we all face. We now welcome Professor Francesco Maggi of the University of Texas at Austin to introduce Alessio Figalli's work and career. Professor Maggi is himself a leading expert in geometric measure theory and the calculus of variations, and a collaborator of Figalli. Prior to joining UT Austin in 2012, Francesco held appointments in Italy and Germany.
Hello, my name is Francesco Maggi, and I am professor of mathematics at the University of Texas at Austin. I've been asked to give this introduction to the work of the 2018 Fields medalist Alessio Figalli for the general public. It's a great pleasure for me, because Alessio is both a dear friend and a companion of many mathematical adventures. It is also a great challenge, because appreciating Figalli's work requires a certain familiarity with what mathematicians do and why their work is important. It is something the general public is not very much informed about, so while introducing Figalli's work, I will also try to talk about the general picture concerning mathematics. Let us start with a bit of context and answer the first question. Where does Figalli come from, mathematically speaking? From the Scuola Normale Superiore in Pisa, Italy, or SNS for short. So SNS is an elite academic institution founded by Napoleon in 1810 on the model of the French École Normale Supérieure, or ENS. The goal of these superior schools was at the time, and still is, that of giving the most advanced education to the most talented individuals of society. Which means that, as a place to go to college, it's a very demanding place, but also a very stimulating place. Interestingly, Figalli was admitted to the SNS mathematics program, although he had a high school diploma in humanities, philosophy, history, ancient Greek, Latin, and so on. So not exactly the technical preparation you would hope to have for thriving in such a competitive mathematics program. In this respect, Alessio likes to tell the story of how much he had to work. He never had to work so much his entire life, day and night, to catch up with his peers. But don't think about this as a to a frantic effort, I'm sure that Alessio already possessed one of his best qualities, that is an unshakably constructive attitude towards problems, about which we will say much more later on. Figalli emerged from SNS as one of the strongest students of his year, and immediately moved to the next stop of the process of becoming a mathematician, that is, graduate school. This is where aspiring mathematicians finally get in contact with modern research. Typically, as an undergraduate student, you hardly venture into the mathematics of the 1900s. So this contact with research and modern mathematics is guided by a scientific advisor, who is a sort of mathematical parent to the graduate student. As with biological parents, they can do a lot of damage, but also some good. And their role is definitely really, really important. Why? Because mathematics is fantastically rich of open problems, possible research directions, big questions, and the problem is that not all of them are equally good choices as entry points into research. Why? Because while some directions are ripe of opportunities for interesting discoveries, other directions have been completely exhausted and have little left to offer. So a very old topic beaten to death. This is how a dear colleague of mine once described to me a certain research direction that, of course, was not our research direction. So some directions are manifestly very important for one reason or the other, but despite their huge interest, they have seen no progress for decades. Maybe they are about to bloom, because someone is about to draw an unexpected connection with another field, or is about to introduce a truly original idea. Or maybe things will be stagnant for another couple of decades, maybe a century or two. These are sometimes the time scales of mathematical progress. So, when you are a graduate student, your entry point into mathematics is going to play a very important role in your chances of mathematical survival. And when your graduate advisor puts you on a problem, they are making a very consequential choice. What fantastic advisors Figalli had. Not one, but two. The first advisor has been Luigi Ambrosio from the Scuola Normale Superiore, and the second advisor, Cédric Villani, Fields Medalist 2010, and at the time, professor at the ENS in Lyon. What Ambrosio and Villani did, they put Figalli on one of the hottest topics of the day and of today, that is optimal mass transport. So, after the pioneering work of the Nobel Prize in Economics Leonid Kantorovich in the 50s, starting from the early 90s, people like Jan Brenier, Robert McCann, who is also co-organizer of this workshop, Craig Evans, Wilfried Gambo, and many others, started realizing a whole array of fundamental connections between optimal mass transport and the mathematical theories of fluids, gases, and other dynamical systems, a stream of connections that essentially has kept expanding since then. It was thus a natural choice for Luigi Ambrosio and Cédric Villani, two leading figures themselves in this huge collective effort of understanding the real full scope of optimal mass transport, to put a fantastically promising student like Figalli on the topic. They did not get much time to enjoy the role of lucky advisors, however, since Alessio completed graduate school in the ridiculous amount of time of 8 months, where one usually takes 4 or 5 years to finish graduate school. In any case, Figalli's contributions to optimal mass transport started during his graduate studies and continued throughout his career, and have been so important, so consequential, that the citation for his Fields Medal literally says, for his contributions to the theory of optimal mass transport and its applications to partial differential equations, metric geometry, and probability. This would be a great point to start telling you about Figalli's research, but before coming to that, I would like to tell you about Figalli's mathematical grandparents. On the Italian side, we find the advisor of Luigi Ambrosio, whose name was Ennio De Giorgi, and who has been one of the greatest mathematicians of the 1900s, and also a very interesting figure, who combined an unsurpassed mathematical vision with a very deep insight on the role of mathematics in the sciences and more generally in the body of human knowledge. And in case you wonder, De Giorgi passed away in 1996 when Figalli was just 12, so they never met. On the French side, we have another heavyweight of mathematics, namely Pierre-Louis Lion. Pierre-Louis Lion was the advisor of Cédric Villani and a 1994 Fields medalist. So I think this is a very, very interesting example of a direct lineage of Fields medalists. So Lyons, Villani, Figalli, maybe a unicum in the history of the Fields medal, I don't know. I hope I'm not putting too much pressure on Alessio's graduate students to get the fourth one. Coming back to Figalli's career, After graduating from SNS plus ENS, he spent 2 years in France at top research institutions like the CNRS and the École Polytechnique in Paris. And then, at the age of 25, he moved to the University of Texas at Austin as an associate professor. He spent there the next 7 years, becoming full professor at the record age of 27. He came back to Europe in 2016, joining ETH Zurich, and 2 years later, at the ripe age of 34, he won the Fields Medal. I was about to say he won his first Fields Medal, because actually, having won one at 34, he will still be less than 40 in 2022, and so he will still be eligible for a second one. Of course, I'm sure the rules don't allow for that, so sorry, Alessio, that's it. I should now introduce what optimal mass transport is about. But I also think you must be curious about how I met Alessio. And this is a good story to tell you, to give you an idea both of the exceptional research qualities of Figalli and about the life of mathematicians. So, where did we meet? There is this national workshop in Italy on calculus of variations and geometric measure theory. These are the technical arcane names of our fields of research. This workshop has a long history. It started in 1990 with De Giorgi and his students and has been going on every year since then. It is a very interesting workshop, a mathematical retreat of sorts. Many Italian professors come with their students from all regions of Italy and converge every year to this same hotel near the Dolomites, a beautiful mountain range in the northern part of Italy. So the whole hotel is booked by the conference. No possible distractions with non-mathematicians. And so they spend 1 week, you ask yourself, skiing, hiking, no, talking about mathematics from breakfast time to the wee hours of the night. I know this may sound like a nightmare to you, but this is actually the kind of thing mathematicians love to do. As a young assistant professor back then, I was giving a talk at this national workshop about a recent result I had obtained with Nicola Fusco and Aldo Pretelli about the stability of bubbles. And I mentioned in passing the problem of using optimal mass transport to study the related question of the stability of crystals. But crystals are more difficult than bubbles because bubbles have a lot of symmetries that crystals do not have. So it's really a much harder beast to tame. So I was giving my talk. I was mentioning this optimal mass transport problem when from this crowd of 100 mathematicians, which is not a crowd that makes a typical graduate student confident about asking questions. So from this large crowd, the graduate student Figalli immediately starts asking questions, and very interesting ones. Not the questions you ask to show off that you are able to ask a question or to keep company to the speaker, so to say. These were really the questions of someone who, in that very same moment, had started to think seriously about the problem, about how to solve it. So zero speculation, all action. Immediately after my talk was over, we started discussing in the hotel lobby, and then we worked on it for the rest of the workshop. Then on the train, coming back home from the workshop, and then over Skype in the subsequent weeks. We also involved Aldo Pretelli, with whom I work with on the stability of bubbles, because he also had a lot of ideas about this problem. And we all three joined our efforts for 6 months, and 6 months later, we finally put the last piece of the puzzle. It happened in Edinburgh, past midnight, walking back to the hotel from a pub. So then we could finally take some rest. This is the kind of dedication and enthusiasm that is behind mathematical discoveries. Nothing comes easy for anyone. You have to work hard, but have fun possibly in doing that. So coming back to the hotel lobby, I remember one thing about meeting Alessio at the time. I thought the question was very interesting, but also very delicate. I was not sure at all how much it was workable, and I had my doubts about trying. When I started observing this graduate student, who was just very calmly working on the problem, getting one piece of useful information at a time, trying to slowly build the general picture of what a proof of our theorem could have looked like. He was like a detective, cracking a difficult case, paying attention to the smallest lead, and steadily emerging from the dark. You know that you will need every piece of information, and he was doing this with such a calm, balanced attitude, without any shade of insecurity or of worry about failure or success. I was so fascinated. I have never seen this kind of approach so effective and powerful to a mathematical problem. And definitely I wasn't expecting it from a graduate student. So it was said that genius is wisdom and youth. And when you see somebody so young doing this job so perfectly, then you say, okay, this is really a manifestation of true genius. So I hope you have found these stories interesting in giving you some insight about how mathematicians work and maybe why not some inspiration for your own creative work. Now, I think I cannot wait any longer to tell you about optimal mass transport. Of course, I cannot give you a mathematical lecture on optimal mass transport, but hopefully I can give you a qualitative description, let's say a poetic description of what this is about. So, what is optimal mass transport? It's the art of transporting one distribution of mass into another distribution of mass. In doing that, you pay a price. So, moving a piece of mass from one location to another has a cost that depend, for example, on the distance between two pieces. The closer the pieces, the less the cost. And if you keep track of all the pieces that you're moving, you define what is called a transport map, which brings the first distribution into the second distribution one piece at a time. And each transport map you define as a cost to be actuated. So optimal mass transport is the art of transporting one distribution of mass into another distribution of mass with a transport map having the cheapest cost. Can such optimal transport maps always be found? How do we construct one? Can we construct more than one? What information is hidden into their structure? It may seem a very abstract question, but that's why and how mathematics works. We do certain abstract things because they go to the heart of the matter, and then they can be used in the most different contexts. You look for simplicity because simplicity is what brings you real descriptive power. So, this was optimal mass transport, but how it is related to crystals? I'm talking about crystals because everyone is familiar with their beautiful shapes, and maybe it happened to you to ask yourself, how are these shapes formed? Why do crystals' shapes repeat with such regularity? Crystallographers figured out the reason why in the early 1900s. There is a mathematical relation, a theorem we should say, between the microscopic properties of atomic crystalline lattices and the macroscopic shapes of crystals. So this result is called the Wolf theorem in honor of the German crystallographer who first figured it out. This mathematical theorem, however, is just telling you what is the ideal shape of a crystal, while in nature, in reality, crystals are never formed through an ideal process and are often perturbed by external factors. For example, what happens when an ideal crystal receives a certain amount of energy, E, by heat transfer? The stability question is how much do crystals deviate from their ideal shape, imagine say a perfect cube, when they are energized by an amount of energy E. Of course, you can make experiments and measure the answer, but the question is, does the mathematical model behind Wolf's theorem agree with experiments? Because if it so does, then I can use the model to make predictions, design devices. But if it does not so, then I have to understand how to change this mathematical model, which correctly predicted the ideal shapes, but failed to describe the energized crystals. So, you want to prove stability in order either to validate the model or to understand its limitations. What we have proved with Figalli and Pretelli is that if you give an ideal crystal an amount of energy, then in average its points are going to move by a distance proportional to the square root of the energy E. These shapes are not arbitrary, and the model behind the Wolf theorem is robust. This is our theorem. So, what is the proof and how is it related to optimal mass transport? The idea is to take the energized crystals and consider the optimal transport maps, taking them into ideal shapes. Notice that we know nothing about the energized crystals because the Wolf theorem says nothing about them. It is just about ideal crystals. So in principle, an energized crystal may have a crazy shape with spikes, tentacles, splattered crystals, pieces of crystals all over the place. So we are transporting this unknown configuration, in principle very complex, into the ideal configuration of with an optimal transport map. The fact that the map is optimal and not arbitrarily chosen should imply that lots of geometric information on the shape of the energized crystals are stored into the map. Can we relate the amount of energy added to how much the optimal transport map is moving mass around? That's what we did. The idea of doing this was, of course, a very natural idea, suggested, for example, in certain works of Robert McCann and Misha Gromov. that inspired our efforts. But the problem, of course, was how to make the natural idea work. To do that, you need more ideas. And you want to find them, because this is a bit the point with mathematics. Not always what everyone expects to work ends up working as expected. Let me give you two examples. First, Newtonian mechanics was believed to explain the motion of all celestial bodies, until people find out some intrinsic limitations of Newton's theory, which could be surpassed only with general relativity. A less known example, the fluids equations that we use to understand how planes fly are actually compatible as mathematical models with weird motions, where, for example, you have a fluid at rest, like water in a glass, and then it starts moving without the intervention of external forces, and then slowly comes back to rest. So there are many lessons about nature to be learned behind mathematical phenomena, and lessons about mathematics to be learned taking inspiration from natural phenomena. Coming back to Figalli's work, let me give you other examples of it, in addition to the stability theorem for crystals. Another example of Figalli's work is the work on the semi-geostrophic equations. These are the equations used to model winds on Earth, and are one of the fundamental mathematical tools used in meteorology. Alessio, in joint works with Guido De Filippis first, and then also with Luigi Ambrosio, and with their jointly advised graduate students, Maria Colombo, who were both speakers this morning at the workshop, has successfully bridged the mathematical theory of optimal mass transport into the semi-geostrophic equations, something that people, meteorologists and mathematicians, have suspected could have been done for decades and wanted to do because it would have allowed for a better computational understanding of the semi-geostrophic equations. So I cannot really tell you about their work, their mathematical work, but what is computational understanding of the semi-geostrophic equations? Why do we need it? Computational understanding means how do you speak with your computer about the equation? How much should you trust what your computer is telling you? For example, for which time span will the simulation of the computer be accurate? You can ask your computer what the weather will be in 1 month. And if it is a sufficiently powerful computer, it will give you an answer with some hours of computations. But the answer will be wrong. The semi-geostrophic equations are so sensitive that there are theoretical limits to how far in the future you can go before the accumulation of small initial errors, both in the data collection and in the numerical approximation, will build up into macroscopic errors. So it is important to understand the mathematics of these equations in order to have the best possible control on how we instruct our computers and for understanding what are the limits of what they can tell us. So this is why these works of Figalli and collaborators on the semi-geostrophic equations were so important for applications. From the point of view of mathematics, they have a huge value in their ingenuity, inventiveness, and intellectual depth. Mathematicians do not really care about computing future weather. As much as the average folk, they just listen to the weatherman. But at times, they give the weatherman a helping hand. So another area where Figalli has given major contributions is the theory of free boundaries. This is a mathematical theory of evolving, moving interfacings arising in biology, geology, physics. A typical example is ice melting. You can imagine having a column of ice that is melting. At a certain point, 2 columns of ice separate at the tip and the touch. And this evolving surface, with its singularities, is what you call a free boundary. The modern theory of free boundaries has been created essentially in the 80s by Luis Caffarelli, who is also co-organizer of the workshop and the person that attracted Figalli to Austin in the first place. And then Figalli attracted me to Austin. So Caffarelli made many groundbreaking discoveries about free boundaries, but also left open some very interesting questions that have been open for 30 years. These questions have been solved in a whole series of spectacular papers written by Figalli in collaboration with Xavi Cabré, Joachim Serra, Xavi Ros Oton, and many others, where they put this theory in some of its main aspects, at least, into final form, giving us a sharp, complete mathematical understanding of these models. As a final example, I will talk about, very quickly and very superficially, of a joint work of Figalli with Alice Guirne. So this work has given long-sought answers about the following fundamental questions. How is randomness reflected in the distribution of the energy levels of a system? So this sounds a very esoteric question, even more than the problems I've talked so far, which at least pertain winds, melting ice, and crystals. The reason for this abstraction is that this same question talks about many, many different situations. It arises in largely unrelated fields like quantum mechanics, finance, telecommunications, where the relations between abstract concepts like randomness and energy level distributions plays a crucial role, taking different names, of course. I will stop here with my list of examples. The point is that there are too many interesting problems where Figalli has given major contributions together with his collaborators and students, and was vast majority I have not even mentioned in this short introduction for the general public. And indeed, we are having an entire workshop at the Fields Institute this week, although in virtual form, just to discuss the latest developments around Figalli's work. But let me stress to close what is a common trait of all these examples. It is the research of a full theoretical understanding of mathematical models used in the sciences. Why is this relevant? It is relevant because science is not only made by experimental work and collection of experimental data. Experimental knowledge alone has some intrinsic limitations, like it happens with the knowledge of the artisan. At the end of the day, you will have to construct something to see if and how that something works. While theoretical knowledge can tell you how something will work without the need of constructing it for real, but just by constructing it, so to say, in the laboratory of your mind. It gives you predictions with margins of error, of course, and can inform you about decisions about what is worth trying to construct for real. Mathematics is the place where you can do such thought experiments. Actually, mathematics, with its descriptive power, has also broken the barriers of what is accessible to experience itself. No one can experience atoms or galaxies, but the mathematics behind quantum mechanics and general relativity is needed to construct the tools and experimental machinery that gives us information about atoms and galaxies, and to interpret the results of these experiments. Actually, without modern mathematics, it would be impossible to even conceive these experiments and the machinery needed to perform them. I think it is important to realize, in order to appreciate the importance of the work of someone like Figalli, that mathematics is a very pervasive creative force in the sciences. Figalli's work is a monumental contribution to this scientific collective effort aimed at understanding mathematical models and at developing new ones. So, I hope you have enjoyed this talk. I have tried my best to introduce you to some aspects of the work of Alessio Figalli, but also to tell you something about the work of mathematicians and about the extreme vitality and relevance of mathematics for the sciences and for our technologically complex societies. Let me congratulate again Alessio for his Fields Medal, and let me thank you for your attention.
Thank you, Francesco, for that wonderful exposition. It is time now to welcome our special honoree this evening, Alessio Figalli. He will be engaged in conversation by Hannah Fry. Hannah is a well-known broadcast personality and public speaker. She's also a professor of mathematics at University College London. I can't imagine a better person to help us to understand Alessio's perspective on mathematics and on life. Please join me in welcoming Alessio and Hannah for a one-on-one conversation.
Thank you very much, Kumar. Well, I am joined this evening by the man of the hour, Alessio himself, as well as many of you from around the world. I've been keeping my eyes on the YouTube chat that's coming up, and people have been saying hello from Mumbai, from Vietnam. There was even someone saying hello from the cow pastures of Vermont. Didn't know that cow pastures of Vermont had particularly good Wi-Fi, but there we go. You learn every day. Now, as we go through this conversation with Alessio, please do send in your questions. They will get through to us and I can ask Alessio on your behalf. But Alessio, I know everyone is very eager to hear a lot of your thoughts this evening on a number of things. But I wanted, if I may, to just start at the very beginning, if that's all right with you. And I wondered if you can remember the very first piece of mathematics that you came across that you were really amazed by.
Oh, well, when I was a student, actually, I started university, I didn't know that much math. I never studied too much mathematics before. So I was immediately fascinated by this new world. And then growing, already second, third year, I started to see more advanced stuff. I remember, this kind of theorems in function analysis where you have existence of solutions by these abstract methods. And then I also remember, and maybe it's nice to cite this because Cédric Villani will be there later, this theorem of the proof of Sobolev inequality via optimal transport that then also inspired a lot my research that Villani did with some co-authors. I was a third year student and I was just fascinated by how mathematics was so interconnected. So the more I saw, the more I got excited.
In a lot of ways, I mean, that's in some ways quite late. I mean, you were a bit of a late starter when it came to mathematics. Is that fair to say?
Yeah, I mean, I started, as maybe you have seen in the video, right? So as a student, I was studying classics until 18. So it was just around 16 that I started to be exposed to math because of the Math Olympiads. I mean, I found these different problems, different from what you see at school. And what I liked was the challenge. I've never been a competitive person with the others, but I was competitive with myself. And so I like the challenge, just put myself on it and try to do whatever I could. And that was the beginning of being exposed to failure also, because many had to do them, especially at the beginning. But the more you try, the more with time, you start to get some satisfactions and then you get excited. So yeah, I started late, but probably it was a good thing. Sometimes, students get scared by mathematics during the course of the studies. I didn't have too much exposure to mathematics, so in the end, I couldn't hate it either. So it was good.
Yeah. Just right in at the deep end, Leslie, like that. Like that. As you were doing those Olympiads, I mean, I know you spoke there about failure, but did you have success too at that time? How did you do in the Olympiads?
Well, I mean, I would say very well for what I would have expected at the beginning, in the sense, I started from the level of this high school. It was really my first time, and I made it to the level. I think I participated the last 2 years of high school, and the first time I went to the national, I made it to the first, I think 25, which I found amazing. I mean, I've really, and then the second year, I made it a bit better, and then I made it to the team there was a selection that would have been trained for the international competition. So I made it to this group of people that among which then you had to select the top 6. So there was another test, and I made it 7th actually. So I didn't went to the IMO, to the International Mathematical Olympiads, because of alpha point that made me arrive 7th. That's okay. Of course, at that moment I was a bit sad, but that's fine.
Well, where are their Fields medals? That's the question.
Yeah, of course. But no one told me back then, right? So at that moment, I only knew that I didn't make the demo, but it was okay.
But even at that point, okay, so when you're doing these Olympiads, you're 17 years old or so at this point.
Yeah, 17.
When did you decide that you were going to do maths at university, where you were going to properly take it up?
Oh, I didn't know until the last day almost. I remember already during summer, I decided to participate to the examination to enter a Scuola Normale Superiore of Pisa. But still, at that moment, I was doubting a lot. I mean, I participated to that admission, but I also participated to an admission for an engineering school in Pisa, Sant'Anna. So I didn't know. I was like, maybe I do math, maybe I do physics, maybe I do engineering. I mean, I had no clue. And maybe the kind of eureka was when I got admitted to Scuola Normale, but not for any reason. But I just remember how happy I was when I saw my name in the list of students selected. I don't know. I didn't expect that. To be honest, I didn't expect to make it. And I was so happy at that moment. I thought, okay, let's do it. I go for math. Even, but it was also a bit irrational at that moment. But it was a good irrational moment.
I mean, that is an unusual story in a lot of ways to have that last minute decision. I mean, I think lots of people who end up going on to do maths PhDs, they know a bit before. They have like a number of mathematical heroes that they've read about that have inspired them along the way. Did you have that too as you were growing up?
No, mathematical heroes I never had. I mean, I never considered mathematics. In fact, I didn't know. Maybe since I never thought much about mathematics as a job, I didn't even study the life of mathematicians. And to be honest, I didn't even realize that mathematician existed that much. I mean, I thought mathematics was still an old subject stuck many, decades ago. And I mean, that was, ignorance on my side. But it was really with the Math Olympiads that I met students who started to say, oh, I want to do math at the university and then maybe become a mathematician. I was like, what? You can do mathematician? I mean, it was a late discovery and it was a nice discovery. In reality, I never planned my life. I mean, I started mathematics and I didn't think I would go to graduate school or anything else. I just thought, now I do math. I do my undergraduate degree. There is first, you do 3 years, bachelor. And then when I did the bachelor, of course, it was natural to do the master. And when I finished the master, I just want natural to continue, but without really planning. I don't know. I never planned too much. Things came, and in a good way. But I just was. I liked what I was doing, and I just went on. I liked.
So you didn't necessarily choose mathematics; you just never gave it up.
Yeah, probably yes. Well, let's say I made that choice at the very moment, and then I never gave up on that. Yes.
Okay, so during your university days, then, when you were doing your training, were there areas that you felt you were weaker at during your training?
Definitely, yeah. I mean, I switched, right? At the first year, I thought I was better in algebra than analysis. So I thought I'd never do analysis because I'm really not good at it. And then second year, then I started to perform better in analysis. I think the reason was that I trained a lot in analysis, so exercises, and then made me stronger when I reached the second year. And but then going on, I felt like, for instance, I remember exams like in algebra, like algebra geometry, where there were some proofs, some arguments where people say, oh yeah, you prove this by taking this polynomial, and then when this polynomial vanishes is at zero set, and with this we prove the theorem. And I just felt like a miracle. How did they come up with that? And of course, there is never a miracle in mathematics. It's all based on hard work first, and this hard work builds intuition, and then via intuition you construct proofs. So it's not that you wake up at night and some divine illumination tells you how to prove a theorem. But let's say for some areas of mathematics, it felt like that to me, and that's why maybe I avoided them, because I needed to feel the intuition, to touch what I was doing, and for me it was more natural than the analytic path, and that's why I chose my field.
So that's an interesting question, actually, about choosing your field. Did you feel like choosing the field of optimal transport was an active choice, or was it about the people that were surrounding you, the collaborations that were available?
Yeah, no, it wasn't an active choice. I think all the time in life, you also have to be lucky. So, I was in Pisa at that moment, and at that moment, ocean transport was a very hot topic. And there were many PhD students who were working on it. So when I was a bachelor student, I could see some of the PhD students working on this topic, and they will maybe share this at the canteen where we were having lunch or dinner, and they would say, oh yeah, I'm working on this problem, it's so cool. In particular, there was one former student of Luigi Ambrosio, who was slightly older than me, Nicola Gigli, and one day he just told me this in front of the canteen. He was smoking a cigarette, and he told me what he was doing during his PhD. And I found it cool, so I thought, oh, this is a nice problem. And then, kind of coincidence, a few months later, it was when I was going as an exchange student to Lyon. So, in Lyon, then at the École Normale, there were quite a few people working on transport, so notably Cédric Villani, that then later became my PhD advisor, and also Albert Fati, who was my professor and my office neighbor in the École Normale. And so I started to work on optical transport a bit by coincidence because I heard about it, I found it cool, I read a bit like some lecture notes. Yeah, I think it was the right moment. I was at the right moment at the right place. That's also a fact. I think the important thing, I think, fortune. So you need to be lucky in life, but you also have to help it. So on one hand, I was lucky that I found myself in this right moment, right place. On the other hand, the fact that I had all the training needed to work on this problem, that was what also allowed me to quickly start to work on it. So the two things went together, and that's how it happened.
And during your PhD, how was it having two supervisors that were in different countries then? I mean, how did that work?
Oh, for me, it worked super well because they were exceptionally, flexible with me. So I was essentially commuting between Lyon and Pisa. Maybe I was just unlucky in the sense that there was no easy way to commute. Let's say it was not super well connected. But I was spend maybe 2-3 months in Pisa, then 2-3 months in Lyon, and then people, of course, start to make the joke that considering my PhD was not that long, I didn't have to do
I was about to say.
I didn't have to do that much. But essentially, when I was in Pisa, I would meet with Luigi Ambrosio very intensively. We will meet even 6 times a week because we were working on a project. We will meet every day. And then when I was in Lyon, I also could meet Cédric essentially every day. He was at the office. And I still remember that he was very busy, Cédric. So maybe some days he didn't have time for me. And then he would come to my office when I was going back home. He would knock at my door and would say, I'm going back home. Walk with me up to the subway station so that we can discuss math. So we had a lot of discussions between the office and the subway station to try to discuss my math problems.
How long
that was
between the two?
Oh, it wasn't that long, probably 10-15 minutes. It wasn't long, but it was very intense. Like 15 minutes, like blah, 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 and Cédric also is very fast. So I will tell him briefly what I was doing. Say, oh yeah, try this, this, and this, and tomorrow you tell me how it goes. But okay, it worked very nicely for me. I was very lucky that they were both, very supportive. They gave me beautiful problems, and also they made it very easy for me to travel and to discuss with both advisors. And at the same time, also they gave me the flexibility to think about other problems. Like Francesco mentioned this problem about supersymmetric optical transport and crystals. That's something I was doing also during my PhD, and I just told them, I'm chatting on Skype with Francesco Maggi about some problem, and they didn't even ask, okay, what are you doing? They say, oh yeah, Francesco is a great guy, just work with him, it's fine. So said, yeah. Then when I was going back to Pisa, I would meet also with Aldo Pratelli was there. So yeah, it just worked fine. But I think I was very lucky, and also the fact that Luigi and Cédric were also so good friends also helped in all the relation.
I think everything came together quite well, which it must have done, because one of the questions that we had in on YouTube was, how is it possible for anyone to complete a PhD in 8 months? Tell us.
Yeah, well, okay, there is a point, right? So I started doing research during my master, right? So when I was at the École Normale at the last year of my master, I was a visiting student, and I was chatting with Albert Fati and Cédric Villanide, and they already gave me problems to work on. And then this was for the first semester of my master. And then when I back to Pisa, Luigi Ambrosio told me, oh yeah, let's start to discuss also this problem. And this was before I started my PhD. So reality, when I started my PhD, I had already worked on research for 1 year. And so that was November 2006. And the fact that I finished the PhD also is not really my choice. And in the sense that, it was a professor a French professor one day who told me, oh, why don't you apply for a CNRS position? And this was in December, so 1 month after I started my PhD. And I was like, what are you talking about? I mean, I started my PhD 1 month ago. I can apply for a CNRS position. And told me, oh, no, but don't worry. You have zero chance of succeeding. That's clear. But I think it's just good because maybe in a couple of years, because people will have seen you, see your CV, maybe you have more chances. I say, okay, cool. Why not? So I just submit the application. It didn't cost me anything to do it. And also Cedric and Luigi, they were like, yeah, it's good that you try. You have zero chances, but whatever, right? And then, at the moment of the interview, it was 5 months later. And also I arrived there, I had the interview, and I still remember the president of the CNRS committee who looked at me and says, why did you apply? This was the question. And my answer was like, well, to be honest, they told me to. I mean, I didn't really think much. They told me to. I said, yeah, why not? And so they asked me, okay, what are you doing? And then I told them exactly about the problem I was working with Francesco and Aldo about these crystals. I say, yeah, we can already prove it's almost the optimal result. I'm sure we can do the optimal one. I don't know, maybe I did a good interview, whatever. And, people behind me, they supported me. I'm sure, Cedric and Luigi and many others supported me in that moment. And then the committee gave me the position. So the point was that, I had a CNRS position. This was end of April. And I started my PhD in November. So it was in reality 6 months. And then I had no choice, right? I had to start a new job as a CNRS. So I say, okay, now I need to write a PhD thesis. So let's collect everything I've done until now and let's write it down. So, the story is different, right? It's not that I didn't plan to make it so short. I don't plan.
I can imagine that was a stressful couple of months at the end there.
Yeah.
I wanted to ask you about something that has been briefly mentioned already. This idea that one of the results that was mentioned for the Fields Medal that you came up with after a few beers during a night out after a conference. Is that an accurate depiction of what happened?
Definitely, absolutely. Yeah. So also Francesco mentioned that in his video. So you can see that, we are on the same page and I'm not, we were in Edinburgh. There was a beautiful conference there. And it was the three of us, me, Francesco and Aldo, and went in the evening for a beer. And I still remember very well the moment, right? Walking home, we were just walking on the street. And at some moment it was like, wait, why don't we did that in a proof? And it was funny because we didn't speak about math the whole evening. I don't have this memory. I think we have been doing math very intensively during the day. And of course, all the months before. And this is something fun about how the brain works, right? So we spent so much time in front of blackboards, doing Skype, in front of a piece of paper, doing computations, and we got stuck all the time. And then the key idea just came at some moment working, which means that in reality, the brain keeps, working on the background. So it's true that at some moment you can have this eureka moment, but the reality, I think, is that, it becomes because you spent a lot of time before thinking deeply about the problem. But yes, the key idea was just there. And it was funny. I remember we arrived at our hotel in the lobby. And the three of us felt it's gonna work. And we said, okay, now we go to bed. We are not gonna check it because we want to go to bed happy. We're gonna sleep believing that we are right. And then at least until tomorrow morning, we're happy. Then we worry whether we're gonna be happy for longer or not. Once you are happy, I mean, why you should have a crappy night checking at details before going to bed, right? So first you go to bed, then you work. So that's what we did. And luckily the day after the Ethereum was still there. So it was a good moment.
I'm impressed that you could have a good night's sleep, to be honest, after thinking that you'd solved something. I'm impressed, but there we go. Let me talk to you. We've got a couple of minutes left. Let me just talk to you about the medal itself. How did you hear that you'd won? What happened?
Oh, yeah. So I was actually in Durham, UK, because my wife was working there. And we were at home. And then I get this email from the president of the MU, the former president, Mori. And he told me that he wanted to talk to me on Skype. And then I just froze. I was like, my God. Because what else could it be? Why the president could want to talk to you, right? And that's the moment also. It was February. And I remember I called my wife. She reads the email. And then she collapsed on the floor just, like thinking, oh my God. But then we were also, okay, we are not 100% sure yet, right? So we cannot celebrate. So I remember sending an email. It was funny because he asked me, can you tell me which time zone you are so that we can chat on Skype? And then I said, oh yeah, I'm on the UK time zone. You can call me tonight until 8 p.m. and otherwise from tomorrow morning from 7 a.m. And my wife said, what? I mean, come on, he can call you anytime, even at night. And I was like, no, I have a dignity to defend. I mean, no, I have to give him a precise schedule, And but it was a very long night because I didn't get a reply. I think he sent me the message before going to bed. He was in Japan. And so I waited, I woke up. I mean, I didn't sleep almost. And then in the morning I wake up, there is no email still. Finally sends me an email, do you have a time in half an hour? I say, oh, sure. And then, you are at Skype and say, oh, we would like to award you the Fields Medal. And I was like, oh my God. And it was amazing. I never expected that because, maybe it's the kind of thing you don't want to think about. I don't know how to say, right? It's too much pressure. So I always try to do my stuff and do my mathematics